All right, welcome Ralston Valley High School AP Chemistry students to another very exciting lecture in the world of AP Chemistry. This is the first lecture from Chapter 7 on modern atomic theory. Most of this lecture should be review from last year's atomic theory unit. So let's go ahead and get started. The first thing we're going to talk about today is a discussion of electromagnetic radiation and wave behavior. As you saw last year, there is an intrinsic link between the behavior of light and our understanding of what's going on inside of an atom. So during today's lecture, we're going to be talking about some properties of waves and how those properties of waves can be used to help us to probe the inside of an atom to gain a better understanding of atomic theory. So to begin, let's start with some definitions. We're talking next about electromagnetic radiation. That electromagnetic radiation is the propagation of waves which carry energy through space via the electromagnetic field. You can kind of imagine this as an oscillation or an alternation of the direction of the local electromagnetic field as the wave propagates through space. Just like a wave in the ocean, these waves are transverse waves. That is, the direction of propagation, that is the direction of the movement of the wave, is perpendicular to the oscillation. And as we've seen several times before, both in physics and in last year's chemistry class, we can describe those waves via several different properties, the first being the wavelength. We define a wavelength as being the distance between two adjacent crests or troughs of a wave. Now, because this is a length, we measure wavelengths in meters, or for light waves, since these light waves tend to have very, very short wavelengths in the light waves that we're interested in, we'll more often measure them in nanometers, that is, in billionths of a meter. Visible light generally has a wavelength somewhere between 380 nanometers on the violet end of the spectrum, up to about 720 nanometers on the red end of the visible light spectrum. So that's first property, again, is wavelength. We use the Greek letter lambda to signify wavelength in our equations. The next property that we will be discussing about wave behavior is the wave's frequency. We use that symbol there that looks like a V. That's not actually a V, that is the Greek letter nu. So frequency gets symbolized by the Greek letter nu, and a frequency is defined as the rate at which waves pass by per given unit of time. The most common unit of time we'll be seeing here is waves per second. That waves per second, or inverse second, is otherwise known as a hertz. And an easy way to kind of think about frequency is to imagine yourself standing kind of on the edge of the ocean, just watching waves go past you. As you're counting those waves as they go by, the number of waves that go by per given unit of time would be the frequency by which the waves are moving past you. And a third property we'll often use to describe waves is the speed of light waves. Now, because the speed of light is a constant, we give it that symbol c for constant in our equations. The speed of light is a very, very fast speed, the fastest speed that something can move at in our universe, as it turns out, and that is a speed of approximately 2.998 times 10 to the 8th meters per second. And now that we have talked about some of those wave properties, let's have a look at the relationships between those properties of waves. As you see on our electromagnetic spectrum here, this should be a familiar diagram to you from both your physics and chemistry classes last year. How we experience those electromagnetic waves differs based upon the wavelength and frequency of light that we are dealing with. The visible portion of that light spectrum represents only a tiny, tiny fraction of all the different wavelengths and frequencies that exist out there. So when we start off on the very, very long wavelength end of the spectrum over there, we're dealing with things like radio waves. Those radio waves can be hundreds or thousands of meters in terms of the wavelength. And that gives them a relatively lower frequency. Now, note again, though, I say a relatively lower frequency, because even though those wavelengths are very, very long, that speed of light is very, very, very fast. And we might even think about some of the frequencies that we're familiar with if we think about radio stations. If you all tune your radio stations in the morning, as you know you do, to listen to some NPR on the way into your school, you might tune it to a station which is 90.1 on the FM band. That 90.1 is in units of megahertz, mega again being a prefix which means 10 to the sixth. So that implies then that those radio waves that NPR is broadcasting at operate at 90.1 million hertz, or 90.1 million waves per second passing by your antenna receiver there. So a relatively low frequency, but again, keep in mind that these frequencies are always going to be very large numbers that we're dealing with. As we move past the radio portion of the electromagnetic spectrum, we move into the microwave portion of the spectrum. Those microwaves are the same microwaves that are utilized by your kitchen appliance to heat up your food. Those microwave radiations generally have a wavelength of somewhere right around a centimeter or so, or a little bit smaller sometimes. Those microwaves are particularly interesting in that they can excite rotational modes of motion among some molecules, in particular water molecules. So when your water molecules in your food absorb the microwave radiation, it causes them to rotate, and the rotation of those water molecules in your food generates friction, which ends up heating the food in your microwave. Moving further along here, the electromagnetic spectrum, we move into the infrared portion of the spectrum. That infrared portion of the spectrum, we generally will notice its ability to excite vibrational modes of motion among molecules, which then in turn we experience as heat. So the place you've most likely seen this infrared radiation utilized is those heating lamps that restaurants will sometimes use outside on their patios during colder months. And not surprisingly, just past the infrared, we move into the visible portion of the spectrum, starting with the longest wavelength of those waves. That is the red color, which we pick up with our eyes. And we move through the familiar rainbow of Roy G. Biv there, from red through orange, yellow, green, blue, indigo, and violet. And then moving out of the violet end of the spectrum, past where our eyes can detect that light, we move into the ultraviolet, which is again higher frequency and shorter wavelength waves. That ultraviolet radiation is produced in a variety of different processes, including by our sun. And we're now moving into the dangerous portion of the electromagnetic spectrum. That ultraviolet radiation can cause sunburn, which you all know has some fairly dramatic long-term effects on human health. And moving into even more dangerous portions of the spectrum at higher frequencies, shorter wavelengths, we move into the X-ray band. We know now that we're in the very dangerous portion of the spectrum, because when you go to get your teeth X-ray, you might have noticed the dental technician taking your X-rays goes to hide behind a concrete wall usually before they push the button on the X-rays to limit their exposure. And very, very high energy waves here. Past the X-ray band, we move into the gamma ray band. Those gamma rays are produced via a variety of processes in nature, including some processes within stars, as well as in some processes of nuclear decay here closer to home. But again, these are very, very short wavelength waves and very, very, very high energy, high frequency. So to generalize here, if we're looking at our relationships between these variables we use to describe waves, waves which are shorter in wavelength have higher frequencies and carry with them higher amounts of energy. Waves which are longer in wavelength generally have lower frequencies and lower energy. That is to say, there is an inverse relationship between wavelength and frequency, given that all of these light waves are propagating at the same speed, that is the speed of light of 2.998 times 10 to the 8th meters per second. And recognizing that inverse relationship that exists between those two variables of wavelength times frequency, the equation for the wavelength-frequency equation should come as no surprise. We see it there, that is the speed of light is equal to the product of the wavelength times the frequency. And that equation will make sense if we look at this from a perspective of a unit analysis. Wavelengths are, again, length measured in meters or nanometers. And a frequency is generally measured in International System Units of hertz, which are, again, inverse seconds. So if we have a look at the product of the wavelength times the frequency of a particular light wave, we'll notice that the units, when multiplying wavelength times frequency, yield units of meters per second, which, again, is a unit of speed. And we can again see that because the speed of light is a constant, this equation does describe an inverse relationship, therefore, between the variables of wavelength and frequency, such that if the wavelength goes up, in order to keep that speed of light a constant, we would have to see a corresponding proportional decrease in the frequency of a wave of light. That is, the product of wavelength times frequency is a constant. One variable goes up, the other one correspondingly goes down. So now that we have developed an understanding of some properties of waves, let's look to see how scientists developed an understanding of a deeper understanding of the atom and matter by utilizing the properties of light waves as a probing tool to understand their universe. The first modern atomic theorist we're going to be discussing here today is a physicist by the name of Max Planck. And Max Planck was, back in the year 1900, doing some experiments in which he was observing what's referred to as black body radiation. When we say black body radiation, we're talking about the radiation which is emitted by objects as they're heated to incandescence, that is, as they're heated to glow. When we talk about black body radiation, we don't really mean that the body is black in that it is colorless. We mean that it's essentially what we assume to be a perfect absorber of energy radiation. That is to say, a black body radiator is a body which is a perfect absorber. It absorbs all incoming electromagnetic radiation, regardless of the frequency or the angle of incidence. And you've seen evidence of black body radiation in the world around you all the time. If you think about like your toaster oven, as your toaster oven gets heated up, you see that it heats up to the point where it starts to glow. And that glow which you're observing there is the radiation emitted by incandescence, that is, by that essentially black body radiator of your toaster oven. Now, what Max Planck observed from his black body radiation experiments was something that fundamentally changed our understanding of nature and the world around us. And that was that energy did not appear to be emitted as a continuous function. That is to say, the energy could only be released or absorbed by the black body radiator in whole number multiples of some principal fundamental quantity, which was dependent upon the frequency of light being emitted. And from this, he derived what's referred to as Planck's equation, which told him that the energy emitted by a black body radiator was equal to some number n, some integer number n, multiplied by a proportionality constant, which we call Planck's constant. Gets the variable h in these equations, which has a value of 6.626 times 10 to the negative 34 joule seconds, multiplied by the frequency of light. And what that observation told him, that energy was not emitted as a continuum, but instead as distinct chunks or packets, was that energy itself is quantized. That is, it comes in individual unit packets that themselves cannot be further split up. And this was our first piece of evidence, really, that nature itself had distinctly allowed values of energy being transferred rather than a continuum of energy. And this was a big change in the world of physics, which led to the development of what we refer to as quantum mechanics. That quantum is, again, a term which we use to refer to as a unit individual chunk or packet of energy. So now that we've had a discussion of Bohr's discovery of the quantization of energy within blackbody radiation, we're going to move on to a gentleman I'm sure you've all have heard of before by the name of Albert Einstein, who was doing some experiments involving what's referred to as the photoelectric effect. I'm sure you all are familiar with Einstein from his later work on relativity, but as it turns out, this discovery of the photoelectric effect was every bit as important of a discovery within the early 20th century to our understanding of how the world works as his later work in relativity. What Einstein was looking at was a known property of metals that when you expose the surface of a metal to electromagnetic radiation, that is to light, the metal can have electrons ejected from its surface, as the metal atoms have electrons which absorb energy from the incident radiation, and that energy can be used to excite the electrons and move them further away from the nuclei which bind them, causing them to eject from the surface. And again, we call this the photoelectric effect. And what Einstein and others who had come before him had believed was that if you had a lower energy incident radiation, that is lower frequency incident radiation, you could shine a brighter light on the surface to essentially build up enough energy to start ejecting those electrons off the surface. Or alternatively, you could shine the light on the surface for a longer period of time in order to build up enough energy to eject an electron from the surface of the metal. And this was the kind of the working hypothesis that scientists had at the time, involving essentially a continuum of energy being able to be built up to cause the ejection of electrons. But from Einstein's experiments, it turned out that, as he discovered, that was not the case. If you had lower frequency incident radiation, that is lower energy light coming in, it didn't matter how bright the light was or how long you shone the light of the surface. No matter what, up until a certain threshold energy, a certain threshold frequency of incident light, no electrons would be ejected from the surface of the metal. And once you did reach that threshold frequency, if you kept the light at the same intensity, but increased the frequency of incident radiation, rather than seeing more electrons be ejected, instead the electrons which were ejected with an increased amount of kinetic energy. That is, they were ejected with increased velocities. So as it turns out, the kinetic energy of those ejected electrons depended only upon the frequency of the incident radiation, not the intensity of the incident radiation. And what that told Einstein was an idea that kind of is the flip side to Max Planck's discovery. That is to say that Planck had discovered that blackbody radiation itself was a quantized carrier of energy. What Einstein discovered here was that the incident light, that is, light waves themselves, seemed to travel as discrete packets or chunks of energy rather than as a continuum. And this is a discovery here that we see light behaving not so much like a wave as like a particle. And those discrete packets of energy are what Einstein discovered there we now know of as photons, a familiar word for a chunk of light. And to give you kind of an analogy about this discovery, if you can imagine for a moment a sandcastle built on the edge of the ocean and waves traveling towards that sandcastle. Suppose that the sandcastle will require a certain amount of energy to topple over. We could imagine that if wave after wave after wave, carrying with them energy, struck the side of that sandcastle, after many, many, many waves strike the side of the sandcastle, it could reach the point where sufficient energy had been transferred to it to knock it over and cause it to tumble to the ground. But as it turns out from Einstein's discovery, light didn't work the same way. if those light waves didn't carry with them enough energy per wave to eject the electron above that threshold energy, it didn't matter how much light struck the surface of the metal, none of those electrons were ejected. It seems kind of like the sandcastle was impervious to waves below a certain threshold energy. And it was only when a chunk of light with sufficient energy struck the surface that the electron itself was ejected. So again, this is another discovery here that it seems like within nature, energy, whether in the form of blackbody radiation or here in the form of incident light, seems to be traveling as unit chunks. That is to say, light waves themselves are also quantized. And now, having made those observations of the behavior of electrons from the photoelectric effect experiments, Einstein came to a new understanding of the behavior of light in what we refer to as the wave-particle duality, or the dual nature of light. That is to say, light appears to exhibit both wave-like characteristics. It does all the things we know waves to do, like it has a wavelength and a frequency, and it refracts and it reflects. But also, light has particle-like characteristics. That is, it seems to travel as a unit chunk of energy, a discrete packet of energy called a photon. And from this, Einstein came to the realization that we could treat light not just as a wave, but also electromagnetic radiation could be thought of as a stream of photons, each of which carrying with it energy described by the equation from Planck's blackbody radiation equation, that is, energy is equal to Planck's constant times the frequency. And it can be useful for us here as well to rearrange Planck's equation by taking into account not only Planck's equation, but also the wavelength frequency light equation as well, for a new formulation of Planck's equation describing energy in terms of not frequency, but instead in terms of wavelength. And you see us do that derivation here. Simply substituting the expression speed of light divided by wavelength, that is c over lambda, which again is equivalent to frequency, into Planck's equation for frequency yields a new expression for energy, which is energy is equal to Planck's constant times speed of light divided by wavelength. So now we have a means of expressing the energy of a photon of light as a function of its wavelength. Now, note here that we have a new expression for energy, and with this expression we can do something kind of cool. That is to say, we can take probably the most famous science equation of all time, that is E equals mc squared, Einstein's formulation of the energy equivalence of mass, and the expression of Planck's equation we just had derived there, which was energy is equal to Planck's constant times the speed of light divided by wavelength. And we can recognize that because both of those equations solve for energy, we can set them equal to one another. And so a little bit of equation rearranging here yields the expressions over on the right-hand side here. And you see here we can derive an equation here which tells us the relationship that exists between mass and wavelength. And this is a kind of interesting idea that there's some sort of mass-energy equivalence. That is, if we experience changes in energy of a system, it also might suggest to us that the system is at the same time experiencing a change in mass and vice versa. And this idea will be picked up here by our next scientist we're looking at, not just in terms of light behavior, but also in terms of the behavior of all matter. Now, having observed from Einstein's discoveries that light itself exhibited a dual nature, that is, a nature both as a particle and as a wave, our next scientist here, who I apologize for my pronunciation here, Louis de Broglie, hypothesized that if light itself, something we traditionally consider to be a wave, also exhibited particle-like characteristics, what if things we traditionally consider to be particles also exhibited wave-like characteristics? And from this, essentially, de Broglie started with Einstein's equation we just derived on the previous slide, which defined wavelength as a function of mass and the speed of light, but then extrapolated from that to particles that were traveling at speeds lower than the speed of light. And from that we get the de Broglie wave equation, which is wavelength is equal to Planck's constant divided by mass times, not frequency there, that's not new, that's v for velocity. And this gives us a means of calculating the wavelength of a particle as a function of its mass and speed. And this gives us some kind of crazy ideas. That is to say, if light, a wave, also has particle-like characteristics, then what about objects, even things like people, which we traditionally treat more with like the ideas of particle physics? What if those objects also have wave-like characteristics that could be calculated? And that's a kind of weird idea. That is to say, you've never seen me walk through a door and produce a diffraction pattern on the other side as I diffract and spread outwards as a point source wave. So why is it with an object like me, human size, you don't see my wave-like characteristics? Well, as we can see from de Broglie's equation, it has to do with the inverse relationship between wavelength and mass. That is to say, I'm a pretty large object, and because my mass is very, very large, that implies that my corresponding wavelength is very, very, very small. And as you've seen probably from your physics days, waves tend to interact best with objects when the size of the object is about the same as the wavelength of the wave. That's why we see things like bats using very, very high-pitched sounds, very short wavelengths, to cause those waves to bounce off of the surface of the objects which they're searching for, those very, very small insects. Or things like ocean waves, which reflect very well off of large objects, like, say, a big concrete wall beside a pier, but they just kind of pass right through smaller objects or pass around smaller objects. Like if you put like a stick in the ocean, it wouldn't cause that wave to reflect off of the stick. So really, because my mass is large, that implies my corresponding wavelength is very, very small. And as such, my wave behavior isn't really noticeable on my day-to-day human scale size life. But that changes when you look at something like, say, an electron. The mass of an electron is much, 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 much smaller than the mass of a human, and as such, the corresponding wavelength of an electron is significantly larger. And with a larger wavelength, that electron might behave in wave-like ways, it might interact in wave-like ways with objects about the size of, say, the spacing between atoms within a crystal, such that if you pass a beam of electrons through a diffraction grating, on the other side, you can actually observe a diffraction pattern of those electrons, which looks almost exactly like the diffraction patterns which you all saw in your waves labs back in physics days. And that tells us then that really there is kind of a blending or a blurring of the lines between the physics of particles that you all learned during first semester of physics and the physics of waves, which you learned during second semester of physics. That is to say, it's not just light that exhibits a wave-particle duality. That is, it seems all of nature, when we look at it from a quantum perspective, exhibits a degree of a wave-particle duality. Now, the de Broglie wave equation seems a little strange, but if you look at it from a unit analysis perspective, it makes a lot of sense. In particular, if we take a look at Planck's constant, which we remember has units of joule seconds, and we divide that by mass, which is measured in kilograms, times the velocity, which is in meters per second, you'll see that the units all cancel out very, very tidily when we recall that a joule can be expressed in base units as a kilogram meter squared per second squared. You'll see that things cancel out very, very nicely here to yield a unit of meters, which again is a length, a wavelength that we had predicted. So now that we've developed an understanding about the dual nature of waves and particles, we can look now at how we can use wave behavior to probe to a more deeper understanding of what's going on inside of the atom. So we'll be talking next about the model atom produced by a physicist by the name of Niels Bohr back in the year 1912. This Bohr model atom replaced the plum pudding model atom proposed by J.J. Thomson and the Rutherford model atom that immediately preceded it. This is probably the model atom, which is most like what you kind of imagine in your mind when we think about what an atom is like. So the Bohr model hydrogen atom fit data that was provided by experimental evidence involving things like emission spectra. Previously, scientists had thought that when you looked at energy emitted by electrons as they moved about in the atom, they should produce a complete continuous spectrum that is like a rainbow of all different possible frequencies of light. But the Bohr model atom took into account the ideas previously proposed by Max Planck and Einstein about the quantization of energy. That is to say, if only specific allowed energy levels were allowed for electrons to be orbiting around the outside of an atom, then only specific energy level transitions would be observed as electrons jumped from level to level. And as a result, we would expect to see only specific colors of light produced by emission spectra, exactly as you saw during your emission spectrum lab last year. So from a perspective of a Bohr model understanding of the atom, as a photon of light is absorbed by an electron, that electron will move to a higher potential energy state further away from the nucleus. And just like anything you put at a higher potential energy state, it will have a tendency to fall back down. And as that electron falls back down, because energy is conserved, if the electron's potential energy decreases, there must be a corresponding equal amount of energy released as a photon of light. And because only specific energy levels are allowed for electrons, that would imply then that only specific colors of light would be produced via emission spectra within a Bohr model atom. So the Bohr model atom justifies the observed emission spectra of hydrogen. You might remember from our emission spectral lab last year observing those three very clear, distinct emission spectral lines, one of them being red, one of them being kind of bluish green, and one of them being kind of bluey purple. There are a couple of other visible lines if you've got a brilliant eyesight or a really good tool in order to help you observe the spectra within the visible portion of those wavelengths. But those lines we're seeing within the Bohr model emission spectra are only a small number of the many, many different electron transitions that would produce photons of light. In particular, the emission spectra which we observed in lab were part of what we refer to as the Balmer series, which represents electrons falling from higher energy states down to not the ground state, but to the second shell of electrons within a hydrogen atom. We don't see what's referred to as the Lyman series of emission spectral lines for hydrogen observed within the visible portion of the spectrum, where the electrons fall all the way down to the ground state, because with a larger electron energy level transition, we would see a correspondingly higher energy photon of light produced. And as it turns out, those photons of light which are produced within the Lyman series are a higher frequency of light than we can see with our eyes. That is, they're within the ultraviolet portion of the spectrum. And by the same logic, we could see electron transitions that fall to the third energy state, but as it turns out, those are smaller transitions in energy, which result in photons of lower energy light, and therefore they're in the infrared portion of the spectrum. So again, we don't see those as visible photons from those transitions. So again, the Bohr model atom was a really good jump in our understanding away from the idea of a continuum of energy into the world of quantum mechanics, where only specific allowed energy levels exist and are permitted. Now, as it turns out, Bohr didn't just come up with the idea for the model, he also came up with some math to back up his observed data. And this is an equation that works, as it turns out, only for the Bohr model hydrogen atom. Introducing more complicated atoms which have interactions between electrons makes the math of these calculations infinitely more complicated. And so we're just going to focus on the math of just the hydrogen atom here. So the equation that Bohr formulated that gives energy levels available to electrons within a hydrogen atom is given right here. That is, the energy is equal to negative 2.178 times 10 to the negative 18th joules times the ratio of z squared, where z represents the nuclear charge of the atom, divided by n squared, where n corresponds to a positive integer representing essentially what shell number the electron is in. Now, again, because this is only working for the hydrogen atom, in all instances that we're going to deal with here, unless you're dealing with some sort of weird thing like a helium ion or something, which doesn't have extra electrons either, we will be using a Z of 1, that is a nuclear charge of 1, since hydrogen atoms, again, only have 1 proton. Now, a couple things I would like you to note here, in particular, that this calculation here is starting off with a negative sign right there. And what that really tells me is that the potential energy of an electron is going to be lower as the value of n gets smaller. And that should make sense, again, because the potential energy of the electron is decreasing as it makes its way closer and closer to the nucleus. And if you go the opposite direction, kind of considering the other extreme, as n trends towards infinity, that is, as you get larger and larger and larger shell numbers, you get further and further away from the nucleus, the value of n trends to infinity, which means the ratio of z squared over n squared trends towards 0. And as such, that would give us essentially a baseline potential energy of that electron at infinite distance away from the nucleus of 0. So if an electron infinitely far away from the nucleus has 0 potential energy, it should make logical sense then that the potential energy of the electron as it gets closer to the nucleus at lower potential energy should therefore become a more negative number overall. So to finish up this modern atomic theory lecture here, let's go ahead and make a calculation of a change in potential energy as an electron transitions between two energy levels, and at the same time the corresponding energy of the photon of light emitted during that electron transition. Because a change in potential energy could be defined as essentially the difference between the final potential energy where the electron ends up and the initial potential energy where it started, I'm just going to go ahead and essentially use the equation which we introduced on the previous slide and simply calculate the final potential energy and then subtract from that the initial potential energy to determine the change. And I've kind of rearranged that equation for you here to determine that change in potential energy here as being equal to negative 2.178 times 10 to the negative 18th joules times, and then here's where we get the difference between final minus initial here. That is a 1 squared, that's my z squared for hydrogen, because the nuclear charge again is 1, divided by the nf squared, that is the shell number where we end up, minus 1 squared over the initial shell number squared. And let's go ahead and just calculate, just for giggles here, the transition of an electron between the third shell and the second shell. So the change in energy would be equal to negative 2.178 times 10 to the negative 18th joules times, let's see, z squared, which is again 1, divided by the final shell. We said we're going to end up at the second shell, that would be 2 squared, minus 1 over the initial shell number, which was 3 squared. And calculating that value out, we get a value of negative 3.025 times 10 to the negative 19th joules of energy for that transition. And again, that value is negative because we saw a decrease in potential energy as the electron moved to the lower energy shell. Now, because that represented our change in potential energy of the electron, which was a decrease in potential energy, the photon of light which was emitted as that electron transitioned from the higher energy shell to the lower energy shell would therefore have an energy of positive 3.025 times 10 to the negative 19th joules. That is, it would carry with it away that energy equal to the change in potential energy that was experienced by the electron as it transitioned. Now let's go ahead, because we now have a value of the energy of that photon, let's go ahead and calculate the wavelength of photon that we would observe from that transition. So because the energy of photon by Planck's equation is equal to Planck's constant times the speed of light divided by the wavelength, we could rearrange Planck's equation to solve for wavelength, which would yield Planck's constant times speed of light divided by energy. So plugging in our numbers here, we're going to take Planck's constant of 6.626 times 10 to the negative 34 joule seconds. We're going to multiply that now by the speed of light of 2.998 times 10 to the 8th meters per second. And all of that's going to get divided by the energy of that photon, which we have just calculated, of 3.025 times 10 to the negative 19th joules of energy. And we can go ahead and cancel out our units there. Joules cancels with joules, seconds cancel with seconds. We get units of meters out of this. And this comes out to be 6.56 times 10 to the negative 7th meters, otherwise known as 656 nanometers for the wavelength of our light. And if we remember back to our previous slide, we remember that 3 photons of easily visible light were present in that Balmer series of electron transition emissions. And one of those photons of light had a wavelength that put it squarely in the red portion of the spectrum, which, as it turns out, 656 nanometers represents. So what we just observed right there is that as the electron transitions from the third to the second energy shell, that transition is responsible for the red color of light, which we observed as that line in our emission spectra lab last year. So, a big takeaway from this calculation here, if the change in energy of an electron is positive, that implies that the electron must have gained energy. And in order to gain energy, that implies that a photon of light must have been absorbed to produce that electron transition. And conversely, if the change in energy of the system is negative by using Bohr's equation right here, that implies that the system must have lost energy, and a photon of light must therefore have been emitted from the atom as that electron transition occurred. So that is our Bohr model atom that you were introduced to last year, now with some math to back it up. And that's it for this lecture. Thanks for listening.